Hey, my name is Eva, and this is Blond Quantum, the podcast that breaks down quantum technology into real-world business impact. Here, we make the complex simple. No equation, no overthinking. Just insight, innovation, and a bit of humor. So don't worry, you don't need a PhD in physics to follow. In each episode, I talk to founders, scientists, and investors about how quantum is reshaping the industries today, not in some distant future. Oh, and if you hear a black cat purring in the background, that's my co-host, very alive Schrödinger's cat, joining the conversation. Her name is Moon. Let's get started. Okay. Hello, everyone. Welcome to the next episode of Blond Quantum. It's a second episode today of our new startup series. And today with me, my guest is Jerome Paye, co-founder and CEO of Tau from Austin, Texas. Jerome, I need to confess you something. The thing is, this may be the toughest episode for me to get prepared so far. Because you see, I like to think about myself as a half technical person. Like, I hold this computer science degree and so on. And there was even a time in my life when I was coding, mostly on university and probably like 16 years ago. But still, the point is it gave me fun. Okay. But physics, on the other hand, that was tough. I'm not even sure we had there like in physics classes. Well, if we had them, I certainly did not attend them. So, when I read the description first time of a Tau system, let me read that for you, okay?
Okay, sounds
Let
good.
me read that for you.
Yes.
So here, Tau Systems is building the ultimate light source for the semiconductor industry with the potential to extend Moore's law into the next decade. They are developing compact particle accelerators and specialized X-ray-free electron lasers that deliver the power of massive kilometer-long national lab facilities in a footprint small enough to fit inside existing semiconductors fabs. Their core value proposition is solving the economical and physical limits of current EUV lithography, which is the bottlenecks for printing the world's most advanced chip. Okay, do you have any idea how this sounds to business people? Do you have it?
Yeah, I can realize that because it's totally accurate, and you very well summarized what we're doing. But the summary itself is quite complicated. So I'm hoping we can help our audience today to understand better all this.
And definitely we should do that because when I read that first time, and I was thinking again, I like thinking about myself as a half technical person. So if I struggle, then the business people probably have no leg to stand on. And in the ears of business people, I think this sounds like something between, I don't know, intersection of black magic with a Star Wars.
Yes.
Somewhere like that, probably. So listen, how about we're going to break it down for our audience and for myself. I never hide that this podcast is actually a way for me to learn more as well. And I do it with a pleasure. So let's break it down from the scratch. Power systems is the ultimate light source for semiconductor industry with the potential to extend Moore's law into the next decade. Let's start from the Moore's law. Can you please explain this for us?
Yes, Moore's law is an empirical law that was devised a long time ago that says that we are increasing continuously the density of transistors, so the element of electronic chips, on a chip that then goes into a computer. And the density doubles every 2 years. That has been the trend of the industry now for many decades. So it's quite amazing that the industry has been able to stay on that trend and continuously innovate to be able to do that. So that's what the industry is doing now, and they made a big leap with what is called extreme UV, which is the type of light that they're using to print the semiconductor. The printing of semiconductor chips is done with light, which is by itself a very amazing process. And if you use light that is what we call shorter wavelength, which means light that goes with different colors in light, and going towards the violet goes to shorter wavelengths. That means more energy in each of the photon, the grain of light that constitutes light. And so the current lithography is using extreme UV, which is way beyond the ultraviolet, very close to X-rays, but not yet in the what we call X-rays.
And that's what Tau is doing, right?
So what we want to do is go beyond what the lithography process is using and go to light that is closer to X-rays, basically what we call soft X-rays. And the reason for that is
X-rays. That's a nice name.
Yes.
Okay, so you basically trying to produce those soft X-ray lasers.
Yes.
To extend the
More so.
Okay.
Because if you have, with that type of light, you can print finer details on your chip. And because there's a limitation that's linked directly to the type of light you're using.
We need this laser to make better chips.
Yes.
Is that okay? Is that how would you say it?
To pack more computing power on one chip.
Beautiful. Okay, that's what I wanted. Like one sentence was just like super easy for everyone to remember. So if the business people who are today listening to us can only remember one sentence, the sentence should be that Tau Systems is building
the light source to do that. To pack more transistors, more computing power on one chip.
To put more computing power to one chip. Yeah. And that is beautiful. Everyone knows we need more and better chips. So that connection is super clear. Now, Jerome, tell me why this is important. Okay, we want to build faster or better chips. Who can use it? Why this problem is important?
It's very important because with the development of AI, we all hear about building all these data centers. And the more you can pack computing power in a chip, the less chips you need for the data centers. And if you need less chips, you need to make less chips. And so the industry will be able to produce the chips we need to build these AI data centers.
So either the data centers will be smaller or they'll be more powerful.
So if you make them more powerful, you need less of them. And since it takes a certain amount of work and time to make one, if you make one that's more powerful, you're going to get more computing power from coming out of the same industry.
This is great. I also have read somewhere, I don't know if that was on your website or somewhere during the preparation, that you basically building particle accelerators, but miniaturized, like a CERN in mini version.
Yes.
Okay. I don't know if our audience know what CERN is. If not, you can explain it as well.
Yes.
But that is something that really spoke to me. And I was like, wow, but how? Like CERN is such a huge, how you can miniaturize CERN?
Yes.
Please elaborate more on that.
Yes. So yes, CERN is the big particle accelerator that has been built by Europe and is 27 kilometers long and is used to study particle physics. So particles are the components that build an atom. And in particle accelerator, they break those components and then they accelerate them, because if you take these particles, electrons, for instance, and accelerate them close to the speed of light, they start doing very interesting things. And that's why, to get to the edge of physics, humanity has built these very incredible machines that are very, very large, very expensive, but can reach the limits of energy and speed for those particles.
You mentioned CERN, and I mentioned that even before in Europe, but we also have one in US, right?
Yes.
It's SLAC in Silicon Valley, next to San Francisco.
Yes. Yeah, it's in Menlo Park, just in Silicon Valley.
Operated by Stanford.
It's operated by Stanford. There's a difference. CERN is a circle. SLAC is a line, and that goes under the freeway. You can see the sign on the freeway when you drive there. And so it's a linear accelerator, but it's the same idea of taking those particles and accelerating them in very complex structures made out of copper and metal, and creating electric fields that accelerate these particles. So it's the same idea, different application. What the accelerator at Stanford is doing, which CERN is not doing, is they have used these accelerated electrons to create an X-ray laser, so what is called a free electron laser. So they're doing that there. In Europe, they also have one. It's in Hamburg. It's called the Euro-XFEL, European X-ray
I didn't know.
Laser. So it's in Hamburg. It's actually a second generation compared to the SLAC one. And so those are the type of accelerators that we're going to miniaturize. When I say miniaturize, it's not...
Oh, that is a very good question, because You just mentioned all of those European and US huge accelerators. You said that, right? How was that? 125 kilometers?
CERN is 27 kilometers.
20.
Yes, SLAC is only 3.2 kilometers long.
Okay, but still, that's a huge, we talk
Yes.
about huge amount of space. So now we talk about startup.
Yes.
Power systems from Austin, Texas. How you
Yes.
can miniaturize that?
So we're not going to dig tunnels for kilometer-long tunnels. We are using a different method altogether. In the conventional particle accelerators, they have some structure that creates electric fields. So an electric field is what can make a charged particle, an electron, move. And they're doing that in either a copper structure, a machine made out of copper, and they put very large currents on that and radio frequencies to accelerate that. The issue is that if you increase how much power you put in that and how much electric field, at some point you're going to create lightning in your structure. And the lightning strikes are going to destroy the material of your machine. So there's a limit there. You cannot accelerate as much as you would like because of that physical limit. In our case, we're doing something totally different. We are accelerating in a plasma. So plasma is when you take a gas, and then we're using a laser pulse that breaks all the atoms in the gas, and then you have basically a soup of nuclei and electrons all together. And our laser pulses are extremely powerful. When I say extremely powerful, during the laser pulse, we have as much power as, actually we have, I think, 8 terawatts, and the installed electrical power in the US is 1.3 terawatts. So we have 6 times more power than the whole electrical grid in the US. But it's a very short time. Yeah. The duration of our light pulses is, if you write it, you write 0, a dot, and then 13 zeros, and then 25. Okay. That's the duration of our light pulse. So in seconds. So it's 25, what we call 25 femtoseconds. So it's extremely short. But during that very, very short time, we pack enough energy to get a very intense light pulse. And light is actually an electromagnetic wave. So it has an electric field, and that electric field, when it goes into that soup of electrons and nuclei, it moves the electrons, and the electrons are lighter, so they move more than the nuclei. And you create in the gas basically 3D waves, electromagnetic waves. And then electrons, when they see those waves, just like people in Southern California, where I am right now, they like to surf, and they catch the wave, and they surf with the wave. The wave moves at the speed of light in the gas. And so we accelerate the electrons because they surf on a 3D wave in the plasma. Because it's already a plasma, there's no risk of breaking things like I was talking about, these lightning strikes in the machine in conventional accelerators. We don't have that problem because we have already broken everything. We've broken the atom, so there's nothing else to break in that soup I was talking about. There's nothing to break.
Even breaking the atoms is such an abstract.
Yeah.
You think about it, right?
So yes, and so the electrons on those waves get accelerated, and that happens over a few centimeters. So the actual acceleration that we create can be on a few centimeters because we can use electric fields that are 1,000 times more powerful than what can be used in a conventional accelerator. So we can put all this acceleration in a few centimeters and get to the same level of energy. So we get in this building where I am in Carlsbad, we accelerate electrons at 99.99% of the speed of light.
Wow.
Because we use this super powerful laser that we have, extremely short pulses, extremely powerful, and we can do that in a very short distance. Now, the whole accelerator is going to be a little bit bigger than that because we need a laser to do that. The laser is 10 meters long, a few tens of meters. And then once we have the electrons, we have to do something with them. And that also takes a bit of space. But all this fits in a building. I'm in a standard commercial building in an industrial park north of San Diego. And it's all in there.
Thank you for saying it, because that's actually my next question. So I wanted to ask you, how physically small this can be, and what's the size of your fab, right? Do you have big facility and so on? So you said 10 meters.
So yeah, the laser is going to be 10, 20 meters at most, depending on the energy you're going to want. And then you're going to need another 10 or 20 meters after the accelerator. Together, it fits in a building. and no tunnel.
And you don't need it. Don't need it 27 kilometers and so
Yeah.
on. So
Yes.
that's beautiful, and that's a huge innovation. So may I ask you? Okay, so you mentioned the facilities in San Diego. Obviously, I'm so jealous you live there. But tell us a little bit about the beginning. How this
So
all started?
yes, so this started in Austin, Texas. The company was founded by two people. Bjorn Manuel Hegelich is a professor at University of Texas at Austin, and he's a specialist in this technology, in laser-powered acceleration, and is actually, at the time the company was built, he had just established the record in electron acceleration using technology that got the highest energy electron produced by laser at the what is called the Texas Petawatt Laser, which is at the university in Austin. And the other founder is Lukasz Gadowski, who's is from Team Global and has helped bring the initial capital for this company because he is absolutely fascinated by science and he wants to use his the funding he can provide to really push the science towards the extremes. And he saw this technology as something that had been developed in academic labs, has been proven to work from a scientific point of view, but was ripe for industrialization and commercialization. So that was really the idea: take this technology out of a lab and make it into a tool that people can use.
I'm glad you mentioned Łukasz as well, because obviously he has a Polish root, so and I'm common Poles. That's very important to me. It's good to me for me to hear that. Speaking of, you mentioned he bring the capital. Actually, when I was preparing to this discussion, I read that there was a um substantial amount of money. I'm not sure if I can disclose it. Maybe you will say, which make me curious because startup founders usually provide capital on the very beginning, but not on the amount. So
Yeah.
I'm not sure how wealthy Lucas is, but this looks like very substantial amount that any VC could put either on a seed level for deep tech or even Series A if it's not deep tech. So he needs to be really convinced of what he is investing into, right? Is he has a background in physics, or do you know how he and Manuel they met?
I think Lukasz had already invested in another company that was working on nuclear fusion, and Manuel was consulting for him, helping him understand the science and work on that investment. But as they were talking about that, they just realized that there was another huge opportunity based on what Manuel had developed in the lab at UT and in his group and before at Los Alamos National Lab. That opportunity was ripe for a startup and for really trying to take this scientific discovery and turn that into what is going to help, I think, many industries in the future.
Beautiful. And now you leading the ship. So can you tell us how many people do you have in your team right now?
We are 23 people. So we are between Austin, Texas and Carlsbad, California. So in Austin, we're working at the university. Our team there is working hand in hand with the scientific team at UT with Manuel, and we are doing our D upstream D there, and we have also worked on a project with DARPA and the Jet Propulsion Lab to develop the application of this technology to space radiation testing. And I'm sure we're going to we'll talk more about that because that is our first market and first application. And I think we have a big role to play in that field.
I'm really glad you mentioned that. So let's talk about it. Because one of the questions I have for you today is like, who can be your clients or who are your clients? Who can be potentially your clients?
Sorry, the
Clients. Yeah, you mentioned
we're working DARPA and Jet Propulsion Lab, which is a NASA lab in Pasadena, California.
Okay.
That and they have a group there that has been working on space radiation testing for a long time, and they are the ones who make sure that the spacecraft that NASA sends in space are going to operate as they intend to and not be affected by radiation coming from the cosmos or from the sun as they travel in space. So that team is doing that, and we've developed with them a new method to test components here on Earth before they are shipped in space to make sure they're going to operate there. And the standard way of doing this type of testing is to go to one of the few government facilities that we have, back to conventional accelerators that we were talking about before. And for instance, going to Brookhaven National Lab on Long Island, where they have an accelerator that accelerates not electrons like we do or like I was talking about, but they accelerate heavy ions. So ions of many different types of elements. And they send those ions on electronic components and see the effect on the electronic components. In space, you also have ions traveling everywhere. And when they go through a computer chip, they deposit energy there. And that energy can create a current. Then you can have the unfortunate event of turning a 0 into a 1 in your memory. And that can have very bad effects on the computing you're doing in space.
So is the space radiation right now your main focus as a usability of the technology that you're developing?
Yes, it is our first market. It is what we're addressing right now with our first machine that we've developed. We're finishing the construction right now. It's going to be operational at the end of August. We're going to bring customers in the fall to use this.
And who are those customers? You mentioned NASA or NASA subsidiary. That's obvious. Who else could be a customers?
So
SpaceX?
yes,
Is there someone else?
SpaceX. Yes, there are a lot of companies in the space industry. The space industry is booming. We now start talking about developing data center in space. Data center in space sounds like a lot of computer chips, a lot of electronic components that are going to be exposed to radiation. So the market for space radiation testing is just exploding right now. The supply is the same old conventional particle accelerator that the government has developed 30 years ago, and that offers a certain number of hours, and there's no more. So we need to find to break that bottleneck and offer much more testing time for the space radiation for the space industry. And we developed a new method. Instead of using ions, we back to our electrons. We creating little packets of electrons that when they hit the semiconductor component, the chip, they will deposit the energy in the same way as an ion. The difference is that we can accelerate these packets of electrons in our building here in Carlsbad instead of having to go into a very long tunnel in Long Island or at a synchrotron at a cyclotron at Berkeley National Lab.
Jerome, this is fascinating. This is fascinating. Ladies and gentlemen, Tau system make computers safe in the space.
Exactly.
That's how it's.
We will do that.
Okay, so this is really fascinating. And you mentioned also that one of your clients is DARPA. Do you have any other clients, or you can tell us, give us a little bit of visibility, who can be your clients in the future, and what kind of other use cases we can have using Tower System technology?
Yes, so it's all the companies that want to send spacecrafts in space. Our technology, which is a substitute or surrogate for what heavy ion testing is applicable for anything that goes into medium Earth orbit or geostationary orbit and for space travel. When you're closer to Earth, those ions are kind of are blocked by the magnetic fields around the Earth, and so that's less of a problem. But anything that goes at high altitude, higher orbits, and in space travel will be exposed to ions, needs to be tested, and you can't wait for the next time slot at Brookhaven National Lab that maybe in 6 months or 9 months to do your testing if you're going to launch your spacecraft next month. So we need to offer beam time, what we call beam time, so that people can test their components much faster and
This is amazing.
much higher availability.
Basically, anything technical or computational, no, is not the word,
Computational, yeah.
that can go to space. It cannot go to space without your technology in the future, because it will be sensitive to the radiation. So sooner or later, anyone who want to do anything in the space will be potentially your customer.
So yes, they need to design their system so that they will be safe in space, and to make sure that what they're designing is going to be working in space, they need to test it. And so there's a lot of work. This for many years, people have been doing that, but the space industry is just growing so much in the last couple of years, and it's going to only increase and accelerate. So the current supply is just not enough, and we're ready for that, and that's why we're rushing to bring our machine to market and our service to market, and our business model is is to offer the service first, but then to also sell space station testing machines to whoever needs one, because they're going to be customers who have a high volume of testing they want to do, or some of them may also want to keep what they're testing a little bit more confidential than what they can do in a commercial company like us or at the national lab, and they want to have their own testing facility. And that was impossible before because that meant digging a kilometer-long tunnel, which they won't do. But now with us, they can buy from us a machine that will fit in one of their buildings and test that themselves.
In one building.
Yeah.
This is really amazing, and I obviously keep my fingers crossed with you. I think in general public is not aware how much is going on in the space right now and how big industry this is, because we don't see it in the media on an everyday. Well, I mean, we hear a lot about SpaceX and Blue Origin and NASA and so on, but there's, as you said, plenty of other startups and companies are doing it, which we have no idea. I remember 8 years ago, I had the episode when I was relocated to one of the company I work for to Perth in Australia. Perth is a mining city, all tradition of mining with Rio Tinto and so on. But what I did not know when I started to exploring the startup ecosystem there, that there was a plenty of space exploration startup, one of the most popular, and they were doing space mining. How this even sounds, right? Space mining. Yeah, and is a very very existing industry that people are usually not aware about. Okay, so but you said this is a primary market. What's the secondary then?
So this is using just the accelerated electrons. But once we have accelerated electrons, we can generate X-ray light. Actually, in the process of accelerating these electrons, we also generate X-ray light. It's called betatron radiation. And that's because our little electrons keep wiggling, and then they wiggle, they emit light, and they create X-rays. So these X-rays are going to be a good source of light for metrology and inspection for the semiconductor industry. They need to make sure that the chips they're making are to spec, are going to meet the requirements and have the the quality level that they need. When you create computer chips that have such minute details, and the only way to look at them is for some of the testing is to use X-rays. So they need X-ray sources to do that, and they need X-ray sources that are bright enough and at the right wavelength, back to this extreme UV, soft X-ray, etc. And so we are going to create X-ray sources that are similar back to another type of government accelerators called a synchrotron, but we can do that again back into a regular building with a machine that companies can afford to do their metrology and inspection. So that's going to be a first use of this.
And if I'm not wrong, this technology may be crucial for some of the quantum components. Is that correct?
Yes, and
can you just tell us
everything back to quantum? Everything quantum is very small, and very small. If you want to look at something very small, the only way is to use X-rays. And the normal X-ray sources are orders of magnitude less bright than what we going to produce. And so that's going to be the tools that we need to develop quantum and to develop the next generation of computer chips will require this type of light sources.
Okay, so basically here in this modality of the market, if you explore it more, so any single quantum company can be your client. Who else can be your client? NVIDIA can be your client?
Yes, and I think our clients are going to be the people who make the tool to do for the semiconductor manufacturing industry that are used to do the inspection. So we're going to provide to them the light sources that they need that do not exist today, and that they've been begging for to do this type of measurements and photos.
So right now, if you can clarify this for me, because I will be very honest, I have no idea. So those are specialized company right now who are doing those diagnostics of the chips, because I thought when you were talking about it before, my first idea was that the companies are doing it internally during the production. So this is not the case. This is external.
No, they're doing it internally, but in the semiconductor industry, there's a whole ecosystem of companies. Everybody has heard about ASML because ASML is actually printing the chip itself. But before that and after that, in the manufacturing process, there's a lot of steps. There's hundreds of steps, and different companies make the different tools for each of these steps.
I see.
It's very different from the auto industry where I used to work, where you have one company making everything. There you have many, many companies developing extremely specialized tools, and it's their specialty, and many of them have a monopoly for that type of tool, and they all work together in a collaborative way
So
to
this is very visual when you said there's hundreds of different stuff.
Yeah.
Okay. So in producing those chips. So may I ask you on how many steps you can help them? All of them, half of them, one third of them, even one step, but crucial one?
So it's going to be more than one, because in the manufacturing process, at a certain point, they need to inspect what they've done to make sure there's not a defect.
Several times.
And so there's several inspection stations. And then they also do metrology, which is take the chips and then measure them to make sure that what they've printed has the right dimensions. And those are also tools that use X-ray light. And
And again,
where we're
everything
going to,
is so tiny, so
and
measuring
it's
it
all
is
paint. Yes.
not easy. Yeah. Okay. Perfect. That's thank you so much for this clarification. That's give us, at
You're
least
welcome.
me, I hope our audience as well, give us a full visibility of potential here. Is there another market that you want to explore or think about exploring later?
So long term, we know that the lithography step, which is printing the actual chip on the silicon, will need to go to shorter wavelength, to a different type of light than what is currently used. The current system is what is called extreme UV lithography, is absolutely amazing, but it's going to reach its limits. There are physical limits to what it can do, and to go a little bit beyond with that same technology will make the machines just exorbitantly expensive. And so that's not an economically viable path. So we did another big step in semiconductor manufacturing by going to a shorter wavelength. SML has done that recently. That's why they have the most advanced chip, and their equipment at TSMC makes the chips that we have in all our cell phones, iPhones, and it's absolutely amazing, but it's going to have its own physical limit too. To go beyond that, we need to go to a different wavelength. So we need a new light source, because the printing is made by light. And those light sources, they exist in government labs, but they're not practical. And we need to make them something that can go in a fab. A fab is the manufacturing plant for chips.
Thank you for saying it. It's another
It's, yeah,
keywords
yes,
inside the bubble.
yes. So we're going to need to go to a different wavelength to be able to print finer details on the chip and continue on this Moore's law that we started our conversation with. And that to get a light source at those shorter wavelengths, which is now close to X-rays, or even what we call soft X-rays, is going to require technology, because once we have those electrons, so there's another step that has been demonstrated at SLAC and at this Euro X-ray field free electron lasers facility in Hamburg, is once you have electrons, you can send them into a series of magnets and make them go a zigzag path. And when electrons zigzag, they emit light. And if you do everything right, they can emit light in what we call coherently. That means the light is all the same coming from all these electrons, and that actually creates an X-ray laser. And these X-ray lasers are the type of light sources that we're going to need to go another major step in the computing power we can pack on one chip.
This is amazing. And this is something that you currently work on, right?
So we're currently working on that. So it will require the accelerator that I was talking about. The laser, we have a laser that drives the accelerator, that powers the accelerator. But then after that, we develop this what is called undulator and create these X-ray lasers. We've been working in Lawrence Berkeley National Lab on a collaboration on that, because they have a system like that. It's still a smaller scale system. It's not in the X-ray yet, but it has all the components and all the technology. We actually just last week they published a paper that on which I'm happy to say that we have several Tau collaborators on that, because we're working with them at Berkeley on that, where they demonstrated for the first time the continuous operation of this free electron laser over 8 hours and 15,000 shots, I think, which is way beyond what anybody else has done before, and shows that this technology is now growing into stability, reliability, and can be on the path to becoming an industrial tool. So that was very important for us
And
to
this is
work on this.
amazing. And congratulations on the paper. Please after the talk, send it to me. I can link it with
Yeah.
a description or even maybe in the video for those who want to read more. And I was gonna say that, you kind of very busy. You have so much different project and collaboration with Berkeley. That's amazing itself. That's a lot for a seed, post-seed
Yeah.
kind of startup, right? And
Yes.
with all of these processes, how far you are today? Are you still in the lab or are you on the edge of commercialization? What's your plans for the next couple of months? Is any new round coming on? Are you raised as well? Are you scale? Are you higher? Tell me.
All of the above, because we have big plans that you've heard, but we want to use space station testing and that market as our proof of business concept, and we're going to commercialize this technology by the end of the year. Have people coming here in Carlsbad and test their system. So we want to get to revenue through that, because
Amazing.
I don't know any better way to prove that we've actually succeeded in turning this lab technology into a
Really.
useful tool than having customers using it. We're going to do that
End of this year.
at the end of this year, and that's when we want to go for a new round of funding, because I think that will be the proof that we are on the path of commercializing and industrializing this very new technology.
Fantastic. So for all the investors who may listen to us today
Yes.
and miss the moment, in a couple of months, Taos Systems is going to raise a new round. So you can
Yes.
reach
Yes.
out now and do not
Yes.
miss that
Yes.
moment.
Please reach out, because it's going to be quite a unique opportunity to develop this technology and be part of this at
And
a very
remember,
crucial point.
essentially everyone who can do something in the future in the space will need technology like Taos systems. So just a reference point. Okay, but that's about the future. And obviously the future is bright and the
Yeah.
plans are amazing. But Jerome, if I can ask you today, what is still your biggest bottleneck? What is still the thing
Well,
that you need to solve before we can scale?
yeah. So I think our biggest bottleneck is what we call the drive laser, which is the source of power for the acceleration. The laser technology has developed tremendously in the last 50 years. We're using this method of creating these extremely short pulses that I was talking about, and these lasers are what we need right now. This is the right driver for space station testing and for our first product. But long term, to grow the power of our systems and get to higher performance and shorter wavelengths for the light we produce, we're going to need more powerful drive lasers. And so we're also developing the laser technology that will make these lasers higher power, higher average power, and lower electrical consumption, because they have to be highly efficient. And we also want to control the cost of these systems, because as we make them bigger, we want to make sure that they are cost effective. So that's where my auto industry background comes back together. We used to make cars that are more powerful, more fuel efficient, and cheaper. It's the same thing. We just
I
need to do
think
that for this technology.
the same pathway. So speaking about this, and you mentioned, Jerome, before about the business model that you have right now is that first you basically operating as a service. So you
Yes.
serve for all this company, and then later on you want to sell the whole machine.
Yes.
Again, 10, 20 meters. So I'm trying to figure out what could be a price of such a machine. Do you have any idea or reference point right now? Are we talking here about thousands of dollars or million of dollars? I know, like
Yeah.
average quantum computer costs
Yeah.
probably $20 million. So where are we on that
Yes.
range of?
So we're in a similar range as the quantum computers or the cryo electron microscopes, and that type of deep tech, deep physics machines that are expensive, because we're building them with components that are coming from supply chains that are very small, and there's no volume to make those very specific components at this point. We're going to change that as we grow and as we sell more machines, but the initial price, of course, is quite high. But that's what we want to do: is build enough machines and sell enough machines that we're going to make the price go down very quickly.
And that's probably natural for new technology, right? And innovation. I mean,
It's
first
so,
computers were also huge and very expensive, right?
exactly, it's the same thing. It's the same thing. Yeah.
Yeah.
We're going
And
to do the same
obviously
for.
that the number may look big, but if we put it on the right scale as well, you cannot dig a tunnel for $20 million.
Yeah, and we're going to offer capabilities that nobody else has. So
And that's even more important.
that's really important, because if there's no alternative, then you may need to spend that much money initially to develop the first applications.
And there is really no alternative? There's no competitors that you have around the world doing similar things?
I
Or
mean,
teams in the lab
I'm saying this technology is going to be the only way to get the
to the
output of
goal.
particle accelerators
Yeah.
in a few $1 million compared to government labs that are in the billions. So our competitor is existing facilities that cost billions, that took a government or several governments pooling their funding together to build, like CERN.
Yeah.
So that's really where we're coming from, is we are orders of magnitude cheaper than the existing technology.
This is amazing. This is amazing, really. Jerome, I must say, I will ask you one last question, but I must say, this time flies very fast, and you have really a good gift of storytelling and breaking things down into simple manners. So I think there will be a couple of really good comparison, which will be viral here. I'm pretty sure about that. But if you tell me, I'm just thinking what should be the last question that I should ask here. I'm gonna look at my notes. But if Tau system succeed in the scale, what would change in the world the most people wouldn't expect? That would be my last question.
I'll put that into what my dream is and what I want for this company.
Good.
We are making particle accelerators affordable and compact. That means we're going to be able to build a lot of these particle accelerators. Particle accelerators are used for discovery at this point. There's a lot of discoveries that are going to be made, and that we're going to be able to do if, instead of having one CERN and one SLAC in the world, we have hundreds of them. That's what
every single bigger and smaller city.
Yeah, and
Multiple of them across every country.
And why do we want to do that? Because with AI is developing right now, as we all know, at incredible pace, but it's all using what we know today. We're going to need to feed AI with new discoveries much faster than the current discovery machines can actually do. So we want at TAV to develop these accelerators, because that's what gets you to the edge of the physical world, the ultra fast, ultra small, the ultra powerful. And that's where we're going to make discoveries, and then give those discoveries to AI, so that we add to what the AI already knows, which is what we currently know, and allow to get to the full potential of what humanity can develop with these new tools.
Do you think in the future the technology can be so popular and affordable that every single university will have one and will train the students based on it?
I think at some point, yes, we'll be able to do that, and that will just totally change the pace of discovery. And we're already talking to universities who are so excited about what we're doing, because they're already telling us, oh, we want to have a machine like the ones you're building, because then we're going to be able to train the students and have new workforce. We're going to then use those systems, and that will expand.
Exactly. Training is super important in developing a new technology. Okay, that sounds really good. And in terms of timeline, where is this future? 5 years, 10 years, 20 years?
This technology is a platform technology with many applications. I talked about a few, because those are the ones we want to focus on, and where we see that we have the market size and the potential that will help us develop all this. But there's no limit to the applications of particle accelerators, because people will never stop wanting to discover new things.
Similar like to quantum computers, right? But
exactly.
I'm just asking you about like a broader bet.
So I think
not talking only about Tau system, in generally in the whole industry that you created here for us. Do you think what is the scale of timeline?
The timeline, the first application is this year, as I was talking about. We're going to bring, I think, the first application of these new light sources in the coming 3-5 years, and then we're going to go from there as we develop the laser technology that drives all this. We're going to grow and answer the need for that next step in the semiconductor industry that is really badly needed at this point. We need to start working on that. The time scale in the semiconductor industry is 10 years to make a big change. So we want to be ready for that.
Amazing.
So we're busy.
Definitely you're busy, and you should be busy, and waiting for you, and keep our fingers crossed for you. And Jerome, thank you so much. Ladies and gentlemen, Jerome Paye, CEO of Tau System. Thank you so much.
Thank you, Eva. It's been a pleasure to talk to you.
That was Blond and Quantum. Thank you for joining me on this journey through the quantum business frontier. If you liked the episode, please review it on Spotify or Apple Podcasts and help more people discover the quantum world without needing to untangle the theoretical physics. See you next time, unless the cat changes the timeline first.